Hi everyone, I'm Emon and I'm a ninth grader currently. Am from West Bengal. So I love to do a bit of Olympiad math and I also have love to do some basic competitive programming in my leisure hours. Although I take it seriously, as you could have found from my blog post that I had written INY this year. So today I will be speaking about on constructions in number theory. So what exactly do I mean? I will just share my screen. 1 second. Yeah, so what exactly do we mean by constructions in number theory? So with constructions in number theory, we mean, as we all know that we often face some questions in Olympiad saying that prove that there exist infinitely many integers satisfying some conditions. We don't care about what the conditions are, and some conditions are given in the problem. Likewise, we also get some questions saying us that prove that there exists an integer satisfying the above conditions. That means that you have to prove that at least, you have to prove the existence of single integer, right? There might be more than that, but you have to give a construction for a single integer and show that it works. Now, what exactly do we mean by construction? So, speaking formally, we represent a number x. We say the number x to be satisfying the conditions if we can represent it in terms of another variable y, where the set of values y can take is infinite. For example, if x is a prime number, x equals p where p is a prime number, then we can say that the set of values, and since we know the set of values prime and the prime state are infinite, therefore we can say that x has infinite value satisfying the
Wait,
condition.
have you changed the slide?
No, the cycle up till now is the same thing.
Okay, can you just wait for 5 minutes? I have to set up my headphones.
Okay. So I hope you already have got a little bit of taste from my blog post. So I will be going on the same lines today. We'll at least try to go on the same lines. And basically, what we will try to do is just to go through some theorems, and afterwards, some of we will prove some. And after at the end of the class, we'll try to do at least 2-3 sums. Now, the two sums that I had posted in the blog, we will do that. We will explain that, and afterwards, and we'll try to solve another problem if possible, if time permits. So that is how I am planning to make it. So now, what we cover? We in this lecture we shall cover the CRT, the Chinese remainder theorem, followed by Lagrange interpolation. Then we'll learn Thew's lemma, and which will be followed by Fermat's two-square theorem and Bell's equation, and then we shall end with a few problems. So I think we can start the session now. Yeah. So CRT. So we can you are seeing a picture, and this is Sun Tzu. So as you could have seen in my blog post, it was Sun Tzu who had actually started it, who had actually proposed a problem, who had actually solved a problem with this particular method of the on the method in which whose lines the proof goes, and he had used this theorem with some specific numbers. For example, if you can look at the theorem, I'll come afterwards, then this a1 and n1s, or ai and ni's, were represented by some numbers like say 3, 4, 5, 6, etc. And he solved the question using the exact same method, and from there on the foundation was laid that we can generalize it into something called the Chinese remainder theorem. So so anyone who can say that what is the statement of the Chinese remainder theorem? Can anyone say what is the statement of the Chinese remainder theorem? Okay, so okay, yeah. So what it states is basically something like this. So it says that if we assume n i's to be a set of pairwise co-prime integers I running from 1 to r, that is basically n1 to nr is a set of pairwise co-prime integers. And what we mean by pairwise co-prime is that ni and nj, for any I and j, the GCD of these two will be 1. And we assume that a1 to ar is some other set of natural numbers. Then we claim that there will exist, there will always exist a unique x in the set which will belong to the set 1 to n1 and the product 1 2 and so on to the product of n1 to nr, n1 into it and so on to nr, such that x is congruent to ai mod ni for I running to from 1 to r. So we have to say that this set of congruencies have a solution, and that solution will lie in the set 1 to the product of ni's. So anyone who can just, I will give you 2 minutes and can think and say the proof of it. At least how, I mean, he will start. I think I will do the proof in the lines of some constructions. So yeah, so can anyone say whether and how we will move it? Okay, so we shall start something like this. We start with the product of ni's and assume it to be the capital N. I assume it to be the capital N. Next, for each k, we define some capital Nk to be n by the small nk. And so what basically, if simplified, then what do we have? The product of n1 to nr only with the nk being excluded. That is basically n1 to nk minus 1, and then nk is excluded, and then nk plus 1 to nr. This will be the product. So now the ni's are relatively primes in pairs, right? We are given that the ni's are relatively prime in pairs. If you look at the statement, that ni's were this let ni n1 to n1 with a set of pairwise coprime integers. These are the pairwise coprime integers. So we have nk and nk to be 1. Why? Because in nk you have all the product terms multiplied except this small nk. Now the small nk is co-prime to n1, n2, and so on to nk minus 1, nk plus 1, and so on to nr. So this nk has no common factor in n1, n2, and so on to nr. So that means that the multiplication here also do not have any common factor, and that is why we have the GCD of the capital Nk and small nk to be 1. So now we can say that there will exist a solution. Nkx is congruent to 1 mod nk. There must exist some solution because nk and the capital Nk and small nk is equal to 1. So does everyone understand why it should hold? Okay, so we now follow this. So we are assuming the unique solution to be called xk. And we claim that we make an outrageous bold claim of y to be the summation of ai ni xi, where I runs from 1 to r. And we claim that this is a simultaneous solution to the given system of congruencies. That means this summation ai ni xi will be congruent to ai mod ni for all I. So this was not so much direct, but if we think a little, then we can find out why this made, because we are trying to make the product something which is the summation of this ai's and ni's and xi's. So we started the proof. So we first prove that, I mean, not really prove, we first observe that n capital Ni will be congruent to 0 mod nj for all j not equal to I. Why? Because in Ni, we have all the in j's except Ni, the small Ni. That means every nj is present except this I. So in Ni, so every nj, small nj will divide Ni, capital Ni, where j is not equal to I. So that is clear, I guess. So then we have y to be the summation of ai ni xi to be congruent to 0 plus 0. So for every I to be till k minus 1, we have this congruencies to be equivalent to 0. And since we are considering mod n small nk, therefore this ak capital nk xk will be the only term which is not divisible by the small nk. Otherwise, all the terms are divisible by nk, small n. And so this term will remain, and from I is equal to k plus 1 to I is equal to r, it will again be this, all be congruent to 0. So that means we are only remaining with the term ak capital nk small xk, mod nk. So is it clear till now? Yeah. So now we recall that we had chosen xk to be the xk to be the particular x for which the congruence capital nk x congruent to 1 mod nk satisfied. Xk was chosen to satisfy this particular x, right? That in capital nk x will be congruent to 1 mod nk. So that means capital nk small xk will be congruent to 1 mod nk. And so if we multiply ak on both sides, then we have ak nk xk to be congruent to ak mod nk, implying that there exists a solution to the given system of congruences. So that means we are getting what we required, right? Because this k can be anything from 1 to r, and we require this thing only, that this summation, because ak nk xk will be the equivalent congruency to this y you can see here, and that is what we had claimed, that y will be a simultaneous solution to the given system of congruencies. So we get what we get, that ak nk xk will satisfy this ak mod nk stuff, and hence we can say that y is congruent to ak mod nk for all k, yeah, from 1 to r. So that means that there will be a solution to the given system of congruencies. So is the existence part clear to everyone? Any questions till this existence part?
No.
Okay. So now we go back to the problem statement. What it had said is, and the theorem, then there exists a unique x. So we have to prove its uniqueness. We have proved its existence, all right, but we have to we are remaining to prove its uniqueness. So it still remains to show that the solution is a unique one. Now assume that x naught is also a solution which is not equal to y, and it is also a solution to the given system of congruencies. So that means we are assuming, for the sake of contradiction, that there exists another integer x naught such that x naught is congruent to y mod nk. So is it clear why we are considering this x naught is congruent to y mod nk? I mean, if x naught is also satisfying the conditions, because it also is a solution to the given system of congruencies, then why is it necessarily why it must be that y should be, it will be congruent to y, because y was also a solution to the system of congruencies, and that means this both will give the same remainders. So we can say the y minus x naught is congruent to 0 mod nk for each value of k. It is very important that we must have this for each value of k from n1, n2, and so on to nr. Each value will divide y minus x naught. And that means what? The product will also divide this y minus x naught. Because why? Because the GCD of ni and nj will be 1. Got my point?
But it can't be. Either it is 0 or it is n1, n2, nr, but it can't be n1, n2, nr.
No, this is that nk was taken to be in a set of natural numbers. So what is the question exactly? Read your question once again.
Actually, in the question, we assumed that y is shorter than n, the product of all the n's. But if we consider that y minus x naught is greater than 0, then y has to be greater than n1, n2, and n2 until nr, which is not possible.
Yeah, exactly like that. I mean, you are precisely so. But since this is y minus x naught is congruent to 0 mod nk, and since every ni and nj will be equal to GCD of that will be 1, that means what? You can't have like this, right? That y minus x naught equals to nk. Then you will have that n2 n1, say. A y minus x naught equals to n1. Now, also here we have that y minus x naught will be some k times n2. But we have what? We have n1 and n2 to be co-prime. That means that there cannot be a common factor. And that is why we can't just say that 2n times n1 or k times n2 will be the thing. So got my point, I guess. So that is why we can say that the product of n1 to nr will divide y minus x naught. And why is it happening? It would not have happened if the GCD of ni and j would not have not been not equal to 1. I mean, if they were not co-prime, this ni and j, then it might so happen that could have happened that this n1 to the product from n1 to nr will not divide by minus x naught. But since the GCD is 1, we must have that n1 to nr, the product of this will divide y minus x naught. So now implying that y is congruent to x naught mod n, because because n1 to nr is equal to n. We had assumed at the very beginning of the proof. This product will be equal to n. We are assuming it. Capital N. So that means what? Now not one thing. This we had what? We had over here this thing that x will belong to the set 1 to n1, n2, and so on to nr. That means it will basically belong to the set 1, 2, and so on to the capital N. So that means that means basically that what we had, yeah. So that means if we have y is congruent to x naught mod n. Now note one thing, that y was what? We are for here y means that this equivalent congruence to which the condition the system of congruences were satisfying it. So that means y should have been lesser equal to n, capital N. I mean, what I mean here we are saying y, but what exactly do we mean by y? Here y means that the remainder which we get, and I mean the y is the very least remainder actually. And so it has to be lesser equal to n, right? Capital N. So everyone understanding why y has to be lesser equal to capital N?
Yes.
Yeah. So that means y is lesser equal to capital N. So now look what one thing. Y is lesser equal to capital N. So x naught must be greater equal to capital N, because we can't have things like this, that y is also less equal to capital N and x is also lesser equal to capital N and both are distinct. We can't have that. Can we have that?
Unless and until x is equal to y, but it is contradiction.
Yeah, that is what you're saying. So that means what? So x is greater equal to capital N since y is lesser equal to capital N. So this implies that either x naught is equal to y or x naught is greater than capital N. Now, if x naught equals y, then we had this is a contradiction since we had assumed x naught to be not equal to y, and thus it's proof its uniqueness. And if x naught is greater than capital N, then it's again a contradiction. Why? Because we had asked for a set. We had asked for the set of that what 1 to n equal to capital N. That x naught will belong to in that set basically. So that means this. So anyone who did not understand the proof or something? Any questions regarding the complete proof?
So the proof was an example of construction in number theory.
Yeah, that is why there might be, it might so happen that I don't really know whether it is the case or not. But it might so happen that there are some other proofs using of CRT. But
Yes,
what
but
we are,
the significance is
yeah,
the
the
significance.
constructions.
Yes, yes.
So we want the class to be considered construction based. So we are also doing it in a constructions manner. Fine. So anyone with any doubts till now? Anyone with any doubts? The uniqueness part, the existence part. Any doubts? Or I shall move on. Okay. So next we move on to Lagrange interpolation. Now, the Lagrange interpolation is not that useful as such, and for this INMO standards or something. But if we focus to IMO standards, then it might so happen that you sometimes have to use the Lagrange interpolation. But the Lagrange interpolation's proof is not at all important. The only thing that is important is its statement and how do you apply it in Olympiads. For example, there was one problem I can remember now. I don't really exactly remember the year if I'm still telling it right. But IMO shortlist 1997. There was a problem where we could have solved it using Lagrange interpolation. So what does exactly Lagrange interpolation state? Okay, before that, let's me tell about some history of Lagrange interpolation, which you might have found it in my blog already. That Lagrange, it was the first Edward Waring in this year 1779, if I am not mistaken, who had found out this formula, theorem, whatever you can say. But he did not publish. Later on, uh, later on, Leonard Euler had found
Joseph Louis
something.
language.
Yeah, sorry.
I guess it
No,
was Joseph
uh,
Louis language.
no. Afterwards, at first, yeah, first it was Edward Waring had found it out. Next, it was Leonhard Euler who had given a easy consequence of this theorem. Means till then, the Lagrange interpolation was not discovered. It was
Uh,
found by
you mean a major
Edward
part of
Waring.
the theorem?
Yeah. So Leonard Euler had, in his one of his research papers, had found out an easy consequence of this, from which Joseph Louis Lagrange got motivated, and he found out this Lagrange interpolation. So the picture on the right is that of Edward Waring, who had actually started this off, and then the left you can see is a common person Lagrange. So what it states is, if a naught till an be distinct complex numbers, and x naught to xn be another set of distinct complex numbers, then there exists a unique polynomial p of degree less than or equal to n, such that p of xi is equal to ai for all I, from 1 to n. Further, if a p of xi equals ai, then we have this further stuff. P of x equals to summation ai from ironing from 0 to n, which is multiplied with the product of x minus xj upon xi minus xj, which where 0 is lesser equal to I, which is not equal to j, which is lesser equal to n. So anyone has any problem regarding the statement? I mean, this might be, yeah. So anyone with any question with regarding this particular formula or particular theorem in statement, basically? Any questions? Okay. So we are not going to prove this because proving this will be really bad. Okay. So, and also the proof is not that important. Proof uses some other things like some graphical stuffs or something. It may be. So if anyone is interested in interpolation stuff, he might also look into some Hermite interpolation, which uses fields. Here we have used complex numbers. There we use the fields is used, right? The capital F. Yeah, fields is used. So if you are interested in interpolation, if you get motivated from it, then you can look into Wikipedia for stuffs like that. Right? The Hermite interpolation. Anyways, so now let's move to another theorem, rather a lemma, we can say. It's a Thew's lemma. So this is Axel Thew, and he was the basic founder, and none had thought of this before. So Thew's lemma is a wonderful result in modular arithmetic, which is also very helpful and useful in Olympiads, and which can give you something really good when necessary. Yes, it is basically helpful for constructions, and we can use it mostly in the cases of say what the squares, perfect, where you have squares. So why we get from the statement. So let n greater than 1 be an integer and a be an integer co-prime to it. So what we have is GCD of a and n to be 1, and n is greater than 1. So then we claim that there exist a positive integers k and l with 0 less than mod k mod l is less than 210. So can anyone tell why is this mod k mod l necessary? I mean, you could have written, right, the positive integers k and oh, sorry. One thing, okay. One correction, please make it. This exist positive integers will not be there. Okay, I mean simply exist integers. I just forgot correcting it. So we said then there exist integers k and l. No, this positive will be cut through. Just strike through it. Okay, so this positive is not necessary. So what will be the statement? Then there exists integers k and l with 0 less than mod k mod l, which is less than root 10, such that this congruence is satisfied. Now, why do we need this mod k and model? Can anyone say? We could have simply written this just as I had written this positive integers k and l with 0 less than k and l, which is less than root 10. But why do we need this mod? And we are erasing this positive thing and we are writing simply mod k mod l. Why do we write that? Can anyone say? Can anyone? Can anyone?
We are talking
Think
about
for it.
remainder like thing.
Yeah. So why
Are
cannot?
you talking about the bound of the 10?
Yeah. So I'm telling that this we could have. Why couldn't we write that there exists positive integers k and l with? I mean, this positive will be cut through
Actually,
now.
because some a would be greater than root 10.
For example, consider n to be 7 and a to be 3. Then just see what you get. N equals 7 and a equals 3. On -4, really? No, not really that. -4 cannot be happening. I mean, -4 is way large. Okay, so mods, I mean, -4 mod 7 is always, I mean, even that doesn't work. So what exactly do we aim at? We aim at making this k and l to be less than root 10 and greater than 0. So look, so first of all, what is root 7? Root 7, integers less than root 7 can
Irrational.
no, no, I mean, integers less than root 7. What are the two possibilities? And greater than 0.
Uh, Either they can be multiple of prime factors of n, or either they are not.
Oh, no, it's not that complicated. I'm saying that what can be the what can be the possible integers less than root, what can I say, root 7. I mean, till now we're considering that what are the positive integers basically say. It can be only two options, right? 1 and 2. Otherwise, if we are taking 3, then it will be root 9, which is greater than root 7. Am I clear?
Yes.
So there can be only two possibilities of positive integers. That is, either it can be 1 or it can be 2. But now
So we take
now
so we
put,
take k and l 1 and 2.
wait a second. Yeah, you can say like that, but that would not also result in a very good thing, because then if you put k is equal to 1, then you will see what? That 3 times k means 3 times 1. 3 times 1 is congruent to -4 mod 7, right? And so the -4, if you take the mod, then we have 4 to be way larger than root n, right? So now another possibility can be what? k equals to 2. That means ak will be 6, which is congruent to minus 1 mod 7, right? So 6 is congruent to minus 1 mod 7. So now minus 1 mod 7. So we will say, so you will argue that if you're taking positive integers, then nothing is working, because L will always get either bigger than that, or will get a way smaller, or it will get negative. So here comes that the modular thing. Why? That is why we need the mod. I mean the absolute value. Here the mod means absolute value. I mean if you take that mod absolute value of minus 1, then it will get 1, which is less than root 7 and also greater than 0. So it might so happen that the congruencies AK or L becomes negative. So in case K and L becomes negative, to avoid the complexities, we do what? We take absolute values on both sides, and then we get what? We get that L mod of L is greater than 0, and again is less than root 7. So am I clear why we are taking these absolute values, and we couldn't just write that positive integers K and L with 0 less than K and L less than root 10?
Yes.
Yes.
So I'm clear, right? Yeah. So that means we have to use this, we can just remove these positive things, positive integers, and we'll write 0 less than mod k model, which is less than root 10, such that ak is congruent to L model. So now the proof. Okay, so we'll move to the proof now. So say this is another thing that you have to be pre-motivated. So why are we doing this? Let m equals to box of the float function of root n. So we are assuming this, that m is the float function of root n. So then what do we have the properties using squares? So we have what? If m is equal to box of root n, then we have what? M is lesser equal to root n is less than m plus 1, right? We have it or not?
What?
Can you just repeat what you said?
We say that m, if m is equals to the box function of root n, then we can say that m is lesser equal to root n is less than m plus 1. Can we say that or not?
Yes.
We can say that, right? So that means, so square everything. So basically square everything. So what, then we have what? You have this, isn't it?
Yes.
Yeah. So do you have m squared to be less or equal to n, which is less than m plus 1 whole square. So now consider all the numbers of the form ax minus y. And why are we considering this? Because we had ak congruent to L mod n, right? So that means basically ak is minus L is congruent to 0 mod n. So that is why we're considering every number of the form ax minus y for all 0 lesser equal to x and y, which is again in turn lesser equal to m. So can anyone say how many pairs, how many ordered pairs x and y we will get from here? How many ordered
2.
pairs? Oh no, come on. I mean every possible. Okay, let's see. No, not like that. See, x can take what values? X can take from 0 to m, right? M plus 1 values. Y can take similarly from 0 to m any value, m plus 1 values. We have x and y, so m will have m plus 1 whole square many values. Is it clear why? So anyone who couldn't understand why it is happening? Just speak out. I mean, I will just tell it once more. No problem. Okay, so means basically I will just repeat once and just move on. That x can take any value from 0 to m, and y can also take any value from 0 to m. That means x has m plus 1 many values possible and y has m plus 1 many values possible, and therefore you get that m plus 1 whole square many ordered pairs x and y are possible. So yeah, that is it. So now look, so m plus 1 whole square many numbers are there, right? So m plus 1 whole square we had from here from the very first line, that m plus 1 whole square is greater than n.
Yes. Then
So
we can use it.
what can we say about the remainders congruent modulo n?
Two of them will be congruent.
Yeah, exactly. So by PHP, you will have that. PHP means the pigeonhole principle. Yeah. So at least two are the same modulo n. So that means there exist integers k1, l1, k2, l2 such that ak1 minus l1 is congruent to ak2 minus l2, and that can happen only if a times k1 minus k2 is congruent to l1 minus l2 mod n. So is it clear why?
Yes.
Now just replace k1 minus k2 by k and l1 minus l2 by l, and you get what was desired. So in the complete proof, I didn't understand. What did you not understand? Can you say? You got right. Okay, so PHP. So do you know what the pigeonhole principle states? So you know that, right? So look. So there is x, then this x minus y can be has m plus 1 whole square many values, right? You understood this? Yeah. So ax minus y will have, if we consider the congruent modulo n, then these things will get more than n, right? But we can have only what values from 0 to n minus 1. These are the possible remainders that we get when we divide by n. But if the number of remainders get increased by from n, then there must have to be two equivalent. Are you getting my point? Just speak up. I mean, you can just speak up. No problem. If you're not understanding, you just speak up. I mean, see, when you divide, wait, I just type it down solution the chat. When you divide some number in, you can have remainders. What you can have remainders from 0 to n minus 1. But since ax minus y is can take greater than n values, therefore the number of remainders will be greater than 100. Oh, it's a one shot. Can you just speak up that where you understanding on and exactly where you are not understanding? Yeah, it's clear, right? I mean, just consider examples and you will understand very easy. They always try to take examples and see. So, any other doubts regarding this question? Anyone? Any other doubts? Or we shall move on. Say with anyone, anything? Okay. So say this is also a construction type. We did give a construction to this, isn't it? Anyone? We gave a construction to this, right?
Yes. By taking a
So what
value.
exactly was the construction?
The construction is actually making proof.
Yeah, so what exactly is the construction here? The very first line is the construction basically, isn't it? And after we are using PHP and stuff like that, but what is the construction here? Let m equals to take root n, and there after you just taking k is equal to k1 minus k2 and l is equal to l1 minus l2, and you
More
do
likely, we are like assuming to take some values of x and y to be shorter than root n.
Yeah, exactly. So that means, yeah, of course, it's not like the previous CRT like proof that will use complete construction, but a little bit of there is in it. Okay. So I will next move on to the Fermat's two-square theorem. So Fermat, no need to give us an introduction. Okay. So what does Fermat's two-square theorem state? It states that if P is an odd prime, then there exist integers x and y such that p equals x squared plus y squared if and only if p is congruent to 1 mod 4. Anyone has any doubt with the statement? I don't think so.
No.
Yeah. So then let's move on to the proof. So can anyone say what the Fermat's Christmas theorem state? There was a session in OMC, right, on Fermat's Christmas theorem. I think the Kazi, Ari, and Amin had taken the class session. I don't really exactly remember, but I think so. So anyone who knows the Fermat's Christmas theorem can state it. Anyone, please, at least give the idea. Okay, so I will say.
Characters.
Yeah, say once more.
It's like it. I don't remember the accurate definition, but I can tell that if there is a mod prime which is congruent to one modulo 4, then it can be denoted as a sum of two squares.
Yeah, that what Neeraj didn't say that. Okay, correct, correct. So it states that I will just show what it states. It states that there exists x such that p divides x square plus 1 if and only if p is congruent to 1 mod 4. So is it clear what this Fermat's Christmas theorem states? I guess the statement of Fermat's Christmas theorem is clear. Okay. So now suppose we have a number q coprime to p. Suppose we have a number q coprime to p. Then by Thew's lemma, we can say what? We can find x and y such that 0 is less than x, y is less than root p, with ay is congruent to x mod p. I mean, here we are assuming this x and y to be just modular stuff. Okay, I have not written it, but you can understand that I mean it. Okay, so can we why can we say this? Can anyone say?
Are you assuming the same x or the different x?
Yeah, just a second. One thing. I will just check. Yeah, so one more again. I will just say another correction you have to make. I forgot to make this ay. It will be not ay. It will be qy. Okay. What was the statement of Thew's lemma? Can anyone please say? What was the statement of Thew's lemma? It stated something like this, right? That a and n are co-prime integers, then there must exist x mod of x and y, such that 0 is less than mod of x and mod of y is less than root n. So exactly we're doing the same thing here. We're taking instead of a, we are taking q, and here instead of n, we are taking p. So is it clear why this is happening? Qy is congruent to x mod p.
Actually, similar problem was proven during surety
Clear?
session. Yes.
Yeah, so that previously. So like that, likewise, we'll say that 0 is less than xy. So this statement is clear, right? Okay. So then we have what? P of divide x square minus q square y square. Just take this x to the left hand side and then you get qy minus x is congruent to 0 mod, and then multiply x minus q yeah, what we have that, yeah, just multiply x plus qy with it. So we're getting this, right? The p divides x square minus q square y square. Okay, so if we have this, then we choose q such that q square is congruent to minus 1 mod p. So this is the construction basically. What are we choosing? We're choosing q in such a way that q square is congruent to minus 1 mod p. Yeah, so q square is congruent to minus 1 mod p. So what is the exact construction of q? Q is a prime, q is a number co-prime to p, and q square is congruent to minus 1 mod p. Am I clear? What is the construction of q? Okay.
Yes.
So now what will we have? From p divides x square minus q square y square, and q square is congruent to minus 1 mod p. What we will have? Say. Say. What will have?
We'll have that y square is congruent to minus 1 mod p.
Oh no, I
1
mean
mod
yeah,
p, sorry.
p divides x square minus q square y square, right? So just replace this q square by minus 1, right? Because we are considering mod p after all. Am I clear why it is happening? Am I clear?
Yes.
Then what will be the next line? P divides what?
P divides k square plus 1.
X square plus y square. Y1. X square plus y square, right?
Yes, because y square is congruent to 1 mod p.
Yeah. P square is congruent. Q square is congruent to 1 minus 1 mod p. Therefore, we have p divides x square plus y square. So anyone with with this line, we get p divides x square plus y square. Oh, also one thing, that why can we take this q in such a way that q square is congruent to minus 1 mod p can be just understood from this um, Fermat's Christmas theorem, that we will have p divides x square plus y square, and similarly we will have p divides q square plus 1. Got my point? So that is why we can say that q square is congruent to minus 1 mod p exists. So from this and from that p divides x square minus q square y square, we have that p divides x square plus y square. So everyone got this, I guess. Yeah. So next we can say that, okay, so now see, p divides x square plus y square, right? Now say that we had 0 less than x and y less than root p. So what will be the range of x square and y square? What will be the range of x square and y square?
It will be like for floor p squared solution, which will be shorter than p squared.
X square, so 0 less than x square is less than p, right? Yeah. So 0 and p. So that means what? Just say that x square plus y square will be less than 2p. Am I clear
Yes.
why that? Yeah,
Yes,
so it will
yes.
be less than 2p. So now see, from 0 to 2p, there can be only one multiple in between, which is one multiple of p, and that is p itself. Because the minimum multiple is 2p after p.
But it can't be achieved.
Yes, that is why I'm saying that we cannot achieve 2p because the stuff will be less
Thus,
than
p
that.
is equal to x squared plus y squared.
Yeah, so that means from here we get that x square plus y square equals p. So everyone understood why this is happening. So everyone understood why this is happening. I will move on after that. We have some problems to do as well. So just say that if you have problem with this thing, why this last line follows or something. Okay, so I guess everyone, I assume
Or
everyone
maybe you should
understood
have,
this.
maybe you should have, maybe
Yeah,
you
go
should
on.
have typed like a instead of q, so less confused.
Yeah. I mean, that was a really bad mistake. I just copied and from there and did it so that I changed this P stuff, but
Yeah, no
forgot to
problem.
do.
But I'm suggesting so
But
that
given a
you can
lecture,
edit.
I get given a lecture in Sophie.
Yes,
Yeah.
I'm suggesting this so
No.
you can.
So I given a lecture in Sophie where I can say that yeah. I just go on. I just interrupting. Sorry. You can go on.
Like I'm saying that I suggested this so that if you upload it on the website, so people would not really can create any confusion.
Oh yeah. So in the website also, I think the blog there was AY, right?
Yes.
Oh, so I will just change it. I will edit it out. Okay.
No problem.
Okay. Yeah.
I'm suggesting.
Yeah. Fine. Okay. That is a mistake. So in the Sophie where I had given a WMP, there also I think this mistake was there, so I forgot just to edit it out. Okay. Anyways, so now let's move on to the Pale's equation. So Pale's equation is a common thing. X square minus y square will be 1, but d is a square free integer. Now can anyone say what is the necessity of d being a square free integer? We could have taken d something, right? Then
If
why are we
d is
taking?
square free, then like we'll have some x squared minus k squared is equal to 1, which is not possible.
Uh, No, that is possible for some.
No, like
No,
it will then
no, yeah,
say
no.
some
Wait,
square is
wait,
of the
wait,
form
wait.
k square plus 1.
Square free integer does not necessarily mean that it will be a perfect square. Square free integer is defined as such that square free integer, say d, can be written as a times k square. Okay, so we can't write this if it is a square free integer. That means what? In the prime distribution of d, we can't have any perfect square. It does not necessarily mean that t will be a perfect square. It might so happen that d is not a perfect square. So for example, suppose we are taking 18, d is equal to 18, then we have what? A factor to be 9, but that can't happen. That is what we get. That 9 is a perfect square. So d does not have a perfect square in his factors, as his factors. Got my point?
Yes.
This doesn't have perfect square as its. So this is how we define a square free integer. That means 18 is not a square free integer, but give me an example. Let me. 14 is a square free integer because 14 contains what factors? 1, 4, 1, 7, 2, and 14. So that 2 and 7 is not a perfect square. So just say like that. So everyone got the statement? What it states?
Yes.
Okay. So this is it. So now we shall move into some problems. But before we move into some problems, anyone can say anywhere from anywhere regarding this today's lecture till now that if they have had any problem in anywhere. For the last time, saying we'll just move to problems and then it will be some hyper stuffs. You have to keep everything. Just I will give you 2 seconds to memorize everything, and then I will say move on to the problems. Just keep in the framework. If I've written it somewhere, just look into it or something. As such, more to add to it, these theorems are really not very much necessary or something like that. But yeah, some theorems like Fermat's 2-square theorem, Thew's lemma, all of them. I mean, just not saying that. But this all will not help you in constructions. You have to construct yourself and then show that that these are holds with the help of these theorems. That means constructions is basically like functional equations. The more you practice, the more you get better at it. Yeah, so everyone just chalk it the things out what you had done today. So we had covered CRTs. The statement of CRT says that if we have some NIs and NIs, where NIs are pairwise co-prime, then we have some unique X in belonging to the set of 1 to the product of N1 to NR, where then this will satisfy the congruencies. X is congruent to AI mod Ni for I running from 1 to R. Then we had Lagrange interpolation. Lagrange interpolation stated something, or something say that we have some AIs to be some complex numbers, and then we had some XIs to be some complex numbers. Then we had then there exists a unique polynomial P of degree less than or equal to n, such that P of Xi is equal to AI for all I. Or also if P of Xi equals to AI, then P of X will be equal to summation I running from 0 to n, which is multiplied with the product of x minus xj by xi minus xj, 0 less than or equal to I, not equal to j, less or equal to n. We moved on to Thew's lemma. Thew's lemma stated something called, say, we have that n greater than 1 be an integer and k a be an integer co-prime to it. Then there exist integers k and l with 0 less than mod k model less than root n, such that ak is congruent to l mod n. I told why these absolute values are required. Then we proved the Theorem and moved on to Fermat's 2-square theorem, which we proved as well. It stated that let P be an odd prime, then there exist integers x and y, such that P is with P equals x square plus y square if and only P is congruent to 1 mod 4. Then Pale's equation, we said that x square minus dy square equals to 1, where d is a square free integer, will have infinite many integers in x and y. So any doubts till now? I don't think so. For the last 30 minutes or so, I will be doing some problems. Try to do 2 or 3, but okay, let's see.
Uh,
So first try
Everything went
this.
nice.
So try this.
Uh, Sorry, but I'm asking some abbreviation related question. What does grade 10 by 6 means?
Well, okay, grade 10 by 6 means that we have you if you have solved all Russian mathematical Olympiads, then we'll see that there are different grades: grade 8, grade 9, grade 10. Not really say grade 9 was there, I don't think so, but grade 8,
Yes,
grade
I've
10.
saw it, but I had this question for a long time.
Yeah, so grade 10 by 6 means grade 10 problem 6.
Okay, thank you.
Okay, so try it for 2 minutes. I will continue after that. I'll continue after. Right. Point. So if anyone has any questions for the next 2 minutes or so, please type it out in the chat because I'm just apply my headphones for 2 minutes. Just type it down in the chat if you have any questions related to this. So you guys said that there's no problem with the CRT Lagrange Interpolation Theorem equation. But this problem does not require much things as a theorem. You have to do your construction, as I said. The more you practice, the more you get better at it. So you have to make some constructions around that will be, but it will completely depend upon you. You can take help, obviously, from this theorem. The the construction will have to be your own at the end of the day.
Can I tell some approach? Hello.
So anyone with any progress?
Can I tell it is a very good basic progress, what I think it would help.
Yeah, go on.
So we have that have that you have to prove the infinitude of such n such that n to the b plus 1 does not divide a to the n plus 1. So it implies we
Yeah.
have to prove infinitude of such n such that a to the n is not congruent to minus 1 mod n to the b plus 1. Now we need to construct such n.
Yeah. So let me give a good construction based hint. Try to consider at first consider a prime p that divides n to the b plus 1, does not divide a to the n plus 1. Then we will have, right, if we can find that there exists such infinitely many such primes, then we can find that n to the b plus if some prime divides n to the b plus 1, it does not divide a to the n plus 1, then it must be so that a to the b plus 1 does not divide a to the n plus 1, right?
Yes, makes sense because then both.
Yeah. So try for 1 minute more, then I will just start the trading session. Also, anyone with any other Nelati, Pranav, Antari, Abhinav, anyone? Is any progress?
We can just select a prime, right?
Yeah, that is what I said. That just select a prime, go on with selecting a prime that divides n to the b plus 1, but does not divide to the n plus 1, and then we can just have to construct something. What after that? Yeah, that makes sense. I mean, afterwards, that is what is going to be useful.
Right. Are we given? Are we free to choose? Are we free to choose A and B?
Well, A and B are given positive integers, so you can't choose that. It will hold for A and B. So what we have to prove is that infinitely many for integers n holds. That means you have to give a construction for n, or if n, basically given a construction for n, not A and B, but you can also give construction for the prime dividing n, and if you can prove that there exists infinitely many primes dividing n to the b, but that does not divide a to the n plus 1, then you can just prove it like a way around that. But I think that the constructions of a and b will not work, because a and b can be any integers, like, as they're given integers, positive integers. So you have to basically give a construction of n and
Can I tell? Can I tell?
yeah, go on.
Then we have that a to the we have that p. We have chosen such primes such that p divides n to the b plus 1, but does not divide a to the n plus 1 for some n.
Yeah, perfect.
Okay.
Okay, just
Then
forget
we
that. At first, I will say. At first, I will just say one thing. Just forget that n to the p, that a p does not to the n plus 1. Just first consider whether p divides n to the p plus 1. Then you can afterwards come to that, right? We divide into two cases. Okay, so first we had what? P divides n to p plus 1, right? So go
yeah
then what we can say from the modulo steps, that n to the b is congruent to minus mod
we
p.
can yes, and we can construct such infinitely many n such that a to the n is not congruent to minus 1 mod p.
So we want to construct a number n such that p divides n to the b plus 1, right? At the end of the day.
Yes, makes
So
sense.
we
Like,
so as yeah, go on.
In this case, the most natural thing we can do is square both the sides, right? And then n to the power 2b
Yeah,
would be congruent to 1 mod p.
exactly. Exactly,
And then we could
that's what was told by
introduce orders and
Nelazari,
stuff.
that you will get that mod order of some n with respect to p to b, because you get what n to the 2b is congruent to 1 mod p. So that is quite understandable why we should square the sides, right? You should square the sides to get a good thing,
Yes,
at least. Yeah. So what we do is
After that, we
you want
can,
an n.
as we have to construct an n, then we can just easily use primitive roots, right?
Yeah, you can use actually things to here. Either you can use primitive roots, you can use Scar's theorem, or you can use Dirichlet's theorem. but I'm going to here today use Dirichlet's theorem today, because I think at least it is easier than the other ones. I mean, it's a bit of overkill, I know, but not much overkill. It is acceptable. For 10.6, it's okay. So primitive roots also work. No doubt. Primitive roots also work, undoubtedly. Yeah. So everyone got my point. Why order of n with respect to p will be 2b? Why is this happening?
Yes.
So everyone got that. If anyone has a problem, let's say, who does not know order, what order is, who does not don't know the definition of order or something like that, speak out. Okay. Okay. So you don't know what order is. Okay. So order is defined as something like this. We say order of n with respect to p. I'll type it out in the chat. Order of n with respect to p is defined as, is defined as the least possible integer n for which a to the n is basically sorry, n2. I am writing n to the a to the n to the that number, say integer k, for which n to the k is congruent to 1 mod p. Mod. Let's say, yeah. Let's say this. So you're getting what's it, Pranav? Yeah. So order of Pn is defined as the least possible integer k for which n to the k is congruent to 1 mod p. Order of p. So here, if we square the both sides, then we'll have that order of p of order n with respect to p is 2b. That is first thing. Next, let p does not write some integer q. Okay. So what can we write from here? So we just say what Fermat's little theorem. Fermat's little theorem stated what? Hello. So what did Fermat's little theorem state? So it stated something like this, right? That q to the p minus 1 is congruent to 1 mod p if p does not divide q.
Yep.
Yeah, right. So that means here we will get what? That n to the 2b is congruent to q to the p minus 1, because we know that q to the p minus 1 is congruent to 1 mod for any q that is not divisible by, and then we can get which can happen only if n is congruent to q to the p minus 1 by 2 mod p. So
And
now
we have
look,
that p
so
minus
we
1
want,
already divides to b.
yeah,
So they both
exactly.
are
So now
equal.
we want the exponent to be an integer, right? We don't need want the exponent to be a fractional thing. Then n would itself become a fraction or something more dangerous. So you need what? You need that
We
to be
need that
divides
to
p minus 1, isn't?
yes,
Yeah, and anyone
yes.
if you are willing to say something, just speak. Turn on your mic, because typing it out will waste your time only. Then that's like this happened. Social pipe. Yeah. So we have to be divides p minus 1. So now we want now what we were at the first we had considered was p divides into the b plus 1, but it does not divide into b plus 1, isn't it?
Yeah.
So now p does not divide a to the n plus 1 means what? A to the n plus 1 is incongruent to 0 mod p.
Yes.
Okay. So then means what? We take n, so with that is the basic construction. Second step, we take n in a such a way that p minus 1 divides n. P minus 1 divides n. So everyone got it? What is the construction here?
Yes.
Yeah, p minus 1 divides n. So now let n equals p minus 1 times r for some r, because since p minus 1 divides n, then it will be some p minus 1 times r, right? So then we have what? A to the n plus 1 is equal to a to the p minus 1 times r plus 1. Now see, a to the p minus 1 is congruent to 1 mod p. That means a to the p minus 1 times r is congruent to 1 to the r. That means will be congruent to 1 simply as well. And then hence we can get a to the p minus 1 times r plus 1 will be congruent to 1 plus 1, which equals 2, which is not congruent to 0 mod p, right? Is line clear? So anyone who can understand this line, because we'll move along these lines after that. So again, everyone has understood this. Okay. So now we make following constructions. So now we can conclude with now here we have the constructions that are working. We will note down one by one. Firstly, n is congruent to q to the p minus 1 by 2. That is the first thing we have done, right? Here, that n is congruent to p minus 1 by 2b. Yeah. N is congruent to p minus 1 by 2b mod p. The next construction is n is congruent to 0 mod p minus 1. Why? Because we said that minus 1 divides n. Assumed it, right? And next, p is congruent to 1 mod 2b. Why? Because p minus 1 to be divisible by 2b. So that the exponent over q is some integer. So any doubts regarding the constructions?
No.
Yeah. So now, why will this hold? Necessary, I guess. So every met the question. So the above two are okay. It's the last thing hold that is not that obvious. That means it might not happen. It could have happened, not happened otherwise if Dirichlet's theorem is not there. P is congruent to 1 mod 2b. So anyone who knows what the Dirichlet's theorem of on arithmetic progression state.
I don't really know what Dirichlet's theorem is.
Okay, so see, Dirichlet's theorem on arithmetic progressions and Dirichlet's theorem on AP states that if you have an arithmetic progression, say a plus, I'm just writing the chat, a plus b, a plus 2b, and so on to a plus nb, and then again it will continue like that. If you have the AP, then there will exist infinite. To add to it, a and n and b are, I guess, second, are both wrong, I guess. Yeah, I think this is a statement. I don't really think. Just a second. Yeah. So whatever, where, yeah. So A and D are co-prime. Then we can say that A plus D, A plus 2D, and so on to A plus ND, and then again it will continue. This infinite sequence is an arithmetic progression. So this infinite AP will contain infinite many primes. This is what the Dirichlet's theorem state on arithmetic progressions state. So is the theorem clear? Is the statement of the theorem clear? So just say it once again. If A and D are co-prime and you have an infinite sequence of arithmetic progression like A plus D, A plus 2D, and so on to A plus ND, and it will continue like that for an infinite instance, then you have infinitely many primes in this sequence, in this AP. This is the Dirichlet theorem. So anyone is in doubt with the statement? So everyone understood what the statement is, because otherwise I can say why P is congruent to 1 mod 2B will hold for infinitely many primes. If everybody understood why this, what is the Dirichlet theorem? Anurag, then other stuffs. Niladri, Pranav.
Yeah, yeah.
Clear.
Understood, right? So
Yeah.
it's clear, right? So that's it. So if it's if the Dirichlet theorem is clear, can you say anyone that why this will hold? I mean, it's also easy consequence of the Dirichlet theorem only. So why this P is congruent to 1 mod 2B yield infinitely many primes P?
Well, that's the statement of Dirichlet, right? For any
Yeah,
arithmetic
yeah. So
progression ax plus b,
yeah,
there are
that is what
infinitely
I
many primes.
yeah, that is what I said, but this is in a way around. I just want to know if actually they have understood or not. So that is what I'm saying, that it is also in a way around that we can say it's congruent to 1 mod 2B will yield infinitely many primes P. So everyone get my point why this will hold. Okay, so just take we can say P is congruent to 1 mod 2B. That means we can say that P equals to be x times x1 2bx plus 1 for some x. We can say this, right? Okay, so if we can say 2bx plus
Yes, we
1,
can.
P equals to bx plus 1. If we can say that P is equals to 2bx plus 1, then we had what? Let this 2bx, so x can be anything. Now say 1, we keep a as a derivative. You can see that where I keep a as 1 and this 2d, it will continue and take d as the 2b thing. So what we take is a equals 1 and b equals 2b. So now is say I think this you are getting why this there will be many primes satisfying this congruency, right? Okay. Anyone with any doubt? So that completes our proof. That means there will be infinitely many primes such, and that will give you infinitely many infinite numbers n, right? Okay. So anyone with any doubts in this problem, you can ask her previous page as well. So I just move to the last problem probably. Okay. So just you can say that. Anyway, please, any doubts? Okay. So now another problem, the last of the night. I will say, okay. Romanian Masters 2012, problem 4. So prove that there are infinitely many positive integers n such that 2 to the 2 to the n plus 1 is divisible by n, but 2 to the n plus 1 is not. So someone tell me what the statement means, what the problem statement asks us for. That means we have to prove that there is infinitely many positive integers n such that n divides 2 to the 2 n plus 1 plus 1, but n does not divide 2 to the n plus 1. It does not mean that 2 to the n plus 1 does not divide 2 to the 2 plus 1 plus 1. It rather means that n does not divide the n plus 1. Okay, so I think you can just try it. I will not give 1 minute because very less time is remaining, 8 minutes. So yeah, try it for 1 or 2 minutes. I will just solution after that. At least how you should progress. I mean, typically you have to first make a old claim, and if you are able to make that claim, then the problem falls apart. I mean, it breaks down to absolutely nothing. But that thing you have to the claim that you have to make is a really bold one. I mean, you do it just, and the proof is not difficult. The proof is very easy. Let's try. Yeah, so any progress? Raised hand, Anturi.
Sir, I think Sigmondi works, right?
Yes, Zygmundi
That
works, but
theorem.
we don't need. But I don't want to go to that. But recently, because many might not know what Zygmundi is. Zygmundi really works. I mean, no doubt with that. Zygmundi works. But we can we make it a bit simpler? I mean, can you first find a number n which actually works?
Like, um, first I tried for 1, n equals 1, but I didn't get any conclusion. Then tried for 2, and then for 3. When I tried for 3, I got a prime 19, which divides 2 to the 2 to the n plus 1 plus 1.
Absolutely. Perfect.
I
Perfect. So
think
that means 19 times 3.
that's the best case.
Yeah. So that means the 19 times 3. So that means 57. So you see that we have a number 57 that works. So if you can make a number, something representable with the help of k, then you are done. So what happens is this proof that you can find infinity in numbers with with respect to. So I'll just show the claim. So what do we claim? This claim is the number k satisfies the conditions, then we claim that if k satisfies the conditions, then so does 2 to the k plus 1. Try to prove this. Proving is really easy this time.
Can you show me the problem statement once?
Yeah, just a second. Yeah.
Um, uh, I think I have proved the claim which you made recently.
Yeah, just go on.
Like, if k satisfies the condition, k doesn't divide 2 to the k plus 1, right?
Yeah.
And k does divide 2 to the 2 to the k plus 1 plus 1.
Yeah. Definitely.
Now, if we replace k with 2 to the k plus 1, then the number of the form 2 to the n plus 1 becomes 2 to the 2 to the k plus 1, right? And the proof follows.
So you have to show two places. I'll just show the proof now. We're running out of time basically. Just 1 minute remaining. I will take 10 more minutes, not really 10 more minutes, but I will take a bit of time. So if anyone has a problem, I'm extremely sorry. I'll try to wrap it up. Anyways, so we are saying that if k satisfies the conditions, then so does 2 to the k plus 1. So now let 2 to the k plus 1 equals L greater than some number greater than k. And firstly, since L is not divisible by k, so okay, first well 2 to the k plus 1 equals L, that means we since k satisfies the conditions, therefore k does not divide 2 to the k plus 1. It's right. I'm clear. So k does not divide L basically. And then we can say that 2 to the k plus 1 does not divide 2 to the k plus 1. So got my point? What I'm trying to say?
Yes, yes.
So everyone got the point what I'm trying to say basically. Yeah, so like just a second. He starts saying something. Okay, so yeah, we start on the problem. I'll just ping it. Okay, so firstly, since L is not divisible by k, then we have that 2 to the k plus 1 does not divide 2 to the L plus 1. Okay, so that means what? L does not divide 2 to the L plus 1. Okay, so L does not divide 2 to the L plus 1. Now note something. 2 to the 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 k plus 1 plus 1 plus 1 equals 2 to the k plus 1 times something. Why? Anyone
Because
say
k
why?
divides 2 to because k divides 2 to the 2 to the k plus 1 plus 1.
Exactly. So we have k divides 2 to the k plus 1 plus 1, and that means that 2 to the 2 to the 2 to the k plus 1 plus 1 will be equals to 2 to the k plus 1 times something which we really don't care about. Times something which we really don't care about. Yeah. So after that, we have what? That means what? 2 to the k plus 1 divides 2 to the 2 to the 2 to the k plus 1 plus 1, implying that L divides 2 to the 2 to the plus 1. So up till now, is it clear? So is it clear? Yes, it's clear. So because just replace 2 to the k plus 1 L and in above as do the similar thing. Replace 2 to the k plus 2 to the 2 to the k plus 1 by L. Then you have that L divides 2 to the 2 plus. Oh, extremely sorry. This last one, okay. I will just I will write the mistakes and then send the PDF. Implying that L divides 2 to the 2 to the L plus 1, and here will be another. We will have to add 1 plus 1. Which is I could have just annotated if it was Zoom, but unfortunately we can't. Okay, so we have that L divides 2 to the 2 to the L plus 1 plus 1. So I get, so what we require? We required that L will does not divide 2 to the L plus 1 and L will divide 2 to the 2 to the L plus 1 plus 1. And that means 2 to the K, we that L side, and we are just getting this exact same. That means what? L satisfies the conditions, and that and means what? If k satisfies the conditions, then so does to the k plus 1. So now as the first point we had said was we have to add 1 to the first thing again. Yeah. So as we said, oh, it's just hold. Okay, just a second. Yeah, so you don't need to see the down thing. Okay, something gives us that k equals to 57 works, as we on the trip said that we'll have that something say if you look n equals 3, then you will have some prime factor of 19, and you get 19 times 3 equals 57. So that works. Hence you get infinitely many such numbers, right? So anyone with this, so that will give us that the infinitude, will prove the infinitude of the n. So anyone with any doubt with this problem? Or no, Antari, Pranav. Any problem?
No.
Understood, right?
No. Yeah.
So no, yeah, okay, so no problem, right? Okay, so anyone with any doubt in the complete session? Okay, just I've not completed yet. I will just give some. So there are 3 more, say 5 more problems there with some hints given. I will also share problem set with Israr, who will in turn will share the announcements. So as resources, you can look into Evanchens, the Otis Excel, and this means here the site that the web.blend.cc we had, because the book is often updated year or something like that. So you can get the updated version from this site only. Then I followed from Rohan Goel's anti-construct PDF, the handouts which he had. Cody Johnson's constructions, that is easily available. The first PDF you get when you search construction number theory in the Google is Cody Johnson's constructions. Aditya Khurmi's modern Olympiad number theory. Justin Stevens' Olympiad theory through challenging problems. Obviously AOPS. Wikipedia used mainly for the CRT and basically some history related stuff. So like who actually first discovered something, did not publish it, just like that Fermat's two square theorem and stuff. So these are the basic thing I used. You can also look at into this. The links are given. So I hope everyone enjoyed this class. So now any questions regarding anything, I will gladly listen. Any questions? Even a whole session